Hi students. So in this video we'll see digital to analog converter. So this is a simple block diagram of a DAC having n number of inputs. So these are all digital inputs. So there is a reference voltage and there is a analog output. So the expression for the analog output voltage is given by K times V reference multiplied by the binary values, and this is the weight of each of the binary. So this happens to be MSB B1 and Bn happens to be the LSB. In this, K is given by the gain of the DAC circuit. So we have a few definitions of this DAC. One of them is VFSR, full scale range voltage, which is also given by K times V reference. VFSV, that is full scale voltage with all inputs as high. That's what is given as VFSV. VFSV is usually VFSR minus 1 LSB. So let us try to find out what is 1 LSBs. So this is what is 1 LSB, which is nothing but FSR divided by 2 power n, where this n is the number of bits, and this FSR is equal to V reference if K is 1. So because basically VFSR full scale range is given by K into V reference. If K is 1, then VFSR is equal to V reference. So I am writing this as V reference by 2n. So suppose if the value of n is equal to 3, suppose if you take the value of n as equal to 3 and V reference as equal to 5 volt, then this happens to be 1 LSB will be, so 5 by 2 power 3, which is 5 by 8, which will be, I think it will be 625 millivolts. So let me do it as 5 by 8. So it is 625 millivolt. So this is what is 1 LSBs. Okay, let us take a look at what is the task given in AEC and ME number 13. And these are the specifications given. So K is taken as 1 and V reference is 5 volts, and we are asked to find different parameters for a given value of n, and we are also asked to find out what is V0 for a digital input over here. So this is a different values of n. We are asked to find what is FSR, FSV, 1 LSB and V0 for these inputs. So I am just rewriting the same thing over here. So this is that table rewritten. So VFSR, as we know, so VFSR is equal to actually V reference multiplied by K, which is 1 here. So in this case VFSR is equal to V reference only. So this is 5 volts. So this is in volts. We know that VFSV, full scale voltage, is given by VFSR minus of 1 LSB. So this is 1 LSB less than FSR. So before we find this, we need to know what is 1 LSB for each of the case. So 1 LSB is given by V reference divided by 2 power n. So we know V reference is 5 here. So we have different values of n. So let us find it for 2 power 4 and then 5 by 2 power 8 and then 5 by 2 power 10. Other one is 5 by 2 power 12. So these are different LSB values. So let me do that. It is okay, let me write it as 5 divided by 2 to the power alpha a. Let me just keep giving the value of alpha a. Calculate if a is equal to 4, that is alpha is equal to 4, then it is, I will write it as 0.3125 volt. Now I'll substitute that variable as 8. Now it is 19.53 millivolt. So and then I will substitute that as 10. So if it is 10, it is, okay, let me write it as 4.88. This is now 4.882 millivolt. Then if it is 12, so it is 1.22 millivolt. So you can see the resolution is very fine when the number of bits are more and more. So if there is a LSB change of 1 LSB, then the output the output voltage changes by 1.22 millivolts because it's a DAC circuit. Now what is this VFSB? VFS is actually 5 minus this, 5 minus this, 5 minus this, 5 minus this. So which you can easily do here. It is now 5 minus of 0.3125. So I will get a maximum voltage of, so it is 4.6875 volts, and if it is this, it is 5 minus 19.53 millivolts, which is 4.98047 volt, and here it is 5 minus 4.582 millivolts, which is 4.9954 volt, and here it is 5 minus 1.22 exponential minus 3, it is 4.9987. These are all the full scale voltages you can think of. Now let us try to find out what is this value, what is the output voltage for all these combinations, for all these inputs, which is of 4 bit, this is of 8 bit, this is of 10 bit, this is of 12 bit. So to do that, let us find out how many LSBs this corresponds to. What is the decimal equivalent of this binary number? So we know that decimal equivalent of this number is, this is like, okay, 8421, this is 8421. So these two are 0 0, it is 8 plus 1, this is actually 9. So this is, the input is actually 9 LSBs. So similarly this I can straight away find here. I'll go to this mode. So this base is 3, and then this is a binary number. So let me type, this is binary, which is 10110101. Let me convert into the decimal. It's actually 181. So this is 181. So since only 9 bits are possible, that is 10th bit is a sign bit. So let me just, okay, because I know that this is 10 bit means 2 power 9 is 2 power 9, sorry. So this is actually a 10 bit, this is 1024, the overall thing is 1024, then this will be 512. If this is 512, because I cannot feed this number and get that value, so I'll just do this. So this is how much? So the decimal equivalent of this is 512 plus this number. So I'll make this number, how much is this? 101101. So it is actually, sorry, this is binary. It is this equals, let me find it decimal, it is 45. So how much is this? 755, it is 557. So 557 is the number. Coming to this, this is if it is 12 bit, so then this is 2000, of course 1024 is also 1, 2048 is also, this value is 2048, this value is 1024, and remaining values are, so now let me type it as, okay, this is binary, this is now 11010110 equals decimal. So this is now 214, this is the decimal equivalent. So this is now equal to 6, this is 1, and this happens to be 3, 8, and this is 2, this is 3. So let me just do that. So now it is mode, now it is 1024 plus 2048 plus 214 is this number multiplied by 1 LSB. So 1 LSB is, because each LSB corresponds to 1.22 millivolt into 1.22 exponential minus 3. So this voltage will be 4.008 volts. So corresponding to this, it is 557 multiplied by 4.582 exponential minus 3. It is 2.552 volt. This is the voltage corresponding to this. Corresponding to this, it is these many LSBs into 1 LSB. That is 19.53 exponential minus 3 into how many LSBs? It is 181 LSBs. This is 3.534 volt. how much is this? This is actually 9 into how many LSBs? Okay, 9 LSBs, each LSB is 0.3125. It's actually 2.8125 volt. So this way we can able to find what is 1 LSB, which is given by V reference by 2 power n. So since n is keep changing, it has got different resolutions. 1 LSB, this is 1 LSB for n is equal to 8, 10 and 12. And we are writing what is the decimal equivalent of this binary number, which is 9, 181 and this is 557. In this calc, I cannot get more than 9 bits. So 10th bit is actually a sign bit. So since it is 10 bit, I cannot get the number directly. So what I am doing is I am considering this, and this is 512, and remaining thing is this. I am just adding that, and that comes out to be so and so. Now let us try to find. Okay, that's it. That's how you can able to do the things. So this is what you can just compare with the values that I shared with you people. Okay, fine. Next question is something like this. Now you are asked to, for a 3-bit DAC, the input 8 combinations are given from 000 to 111. There is a DNL given 0, half plus half LSB. Of course, all these DNLs are in half LSB specification. You are asked to find what is the gain and what is the offset error, and of course you are asked to find what is INL. So let us see how to do this. Okay, this is, I just reproduce that values. Now I have also written, because I know this, okay, INL at any bit is given by summation of DNL till that bit. So I can simply complete this by adding all the terms. So here it is 0, and let me write this is 0 now. That's not properly visible. So what is this? This is half LSB, and this plus this is actually minus half LSB. This plus this plus this plus this is again minus half LSB, and this plus this plus this plus this plus this. These two will cancel out. I'll end up with half LSB. Till here, these two will cancel out. These two will add up. It's 1 LSB. You can see here. Till here, these two will cancel out, and these half will add. It will become 1. Till here, it's just the addition of minus half to this. So what is this? Now it is minus half. This is minus half. So INL is nothing but summation of DNL till that point. So what I am trying to do is, I'll just retain this as it is because there is nothing here. You add these two, put it here. You add these 3, put it here. You add these 4, put it here. So that's how it goes. Looking at this, we can clearly see this is how you can plot it on the graph. Suppose you want to plot it on the graph. So these are the ideal values. So this is 0 INL and 0 DNL, because when 0 0 0 it is 0, when it is 0 0 1 it is 1 LSB, when it is input is 2, output is 2 LSB, input is 3, output is 3 LSB. If you want to actually plot the graph, if you want to actually locate where the things are, so now this is my INL. So suppose if you just do this, this is 0, this is half LSB more, this is my actual point, this is half LSB more, then this is actually minus half LSB. So from this value it's actually minus half LSB, and then this is also minus half LSB, it's here, and this is 1 LSB more, sorry, half LSB more. So from the ideal value it is half LSB more. Next it is 1 LSB more, because these are all INLs. So from the ideal value, how much it is more. So this is my 1 LSB more from here to here, and then this is for 110. For 110, it is minus half LSB. It is because this entire 1 centimeter, this is 1 LSB, this is half LSB, and it's again minus half LSB. So this is how we are writing the values. So you can actually find out, okay, the DNL is actually this is your bit, it was supposed to be here, now the DN is half LSB. With this as the bit, the output would have been here, but the output is here, you have minus 1 LSB. So that's what is this, minus 1 LSB here. And then from here, this would have been here, it's there only, that's why it is 0 LSB. From this would have been here, of course, sorry, this would have been here, but it is above by 1 LSB, so that's why it is 1. From here, this would have been here, but it is actually half LSB more, so that's why it is half LSB. So from this would have been here. What has happened here? This is actually what happened. This is half LSB, this is minus half LSB. Some fishy thing happened here. This is, suppose if I just add this, okay, let me just track it here. Okay, now these two have cancelled, this is half LSB, these two have cancelled, it is so and so. Oh, this is plus half LSB, sorry. You can see this is plus half, because when I add this, so here it is getting missed out, so it is not tallying with that. So this is actually, this is not correct, this is the correct one, because while adding I just made a mistake. So these two will cancel out, these two will cancel out, this half will remain here. So this is correct. So from this would have been here, it's actually here, that's why it is minus half LSB. And from this would have been here, but it is, okay, how much is this? Okay, okay, now this is 0 means, okay, now this is not here, this is actually here, this is actually here, this is also not correct. That's fine. So now let me add this. This is going, this is also going, this is again plus half LSB. This is plus half LSB, that's also plus half LSB. You can see this is plus half LSB. Of course, it's not difficult, just hang on. See, here there was an addition problem. See, 0 plus half is half, 0 plus half plus minus, sorry, minus 1 is minus half, this plus this is again minus half, this plus this plus this plus this plus this, so these two will go off and you have plus half. And here this is actually all these things addition, these two will going to add up, these two will cancel out, it is 1 LSB. Till here everything will add up, so it is half LSB. And till here the same half LSB continues. So that's what I have here. So INL is 0 here, INL is half LSB more, INL is minus half LSB, and next INL is minus half LSB, but for 110 it's half LSB more INL. Then for 101 it's 1 LSB more here. This is 101, it is 1 LSB more. For 110 INL is half LSB more, you can see it's half LSB more. And for 111 it is again half LSB more, it's half LSB more. So this way you can able to find INL and DNL and the plot. Okay, fine. So let us find out for this. So let me just plot it. So it just requires, so this is 0 0 0 and this is, let me mark the points. This is 0 0 1 0 1 0 0 1 1 1 0 0 1 0 1 1 1 0, this is 1 1 1. So this is 0 LSB, 1 LSB, 2 LSB, 3 LSB, 4 LSB, 5 LSB, 6 LSB, 7 LSB. Okay, coming to plotting. Okay, let me write the ideal values. So ideal values are this red one, this one, and for 2 LSB it is 2 here, and for 3 LSB it is 3 here, for 4 LSB it's 4 here, for 5 LSB this is 5, you can see this is 5, this is 5, and this is 6, this is 6. See here? This is 7, that is 7. So it's actually a line of slope 1. These are the ideal values. These are the ideal values. So what is your INL given? So this is the values that is available. Let me write it here. First is in the 0 itself I have half LSB more. Can you see it is half LSB more? This is half LSB more. For 0, 0, 1 it is minus half LSB. Can you see this is 0, 0, 1, this would have been the value, but it is minus half LSB, it's here. Then for 0, 1, 0, for 0, 1, 0 it's 1 LSB more. From this ideal value it's actually 1 LSB more. This is the 1 LSB more. Then for 0, 1, 1, for 0, 0, for 0, 1, 1 it is 0 LSB. 0, 1, 1 it is 0 LSB, it is on the same line. Next it is for 1, 0, 0, it's actually minus 1. So for 1, 0, 0, this would have been here, but it is minus 1 LSB less. Then it is for 1, 0, 1, it is 0, so it's here. Then for 1, 1, 0, it is 1.5. This is 1, 1, 0, it's 1.5 LSB more, so that is, it's here. Then for what? For 1, 1, 1 it's minus 1 LSB. For 1, 1, 1 it is minus 1 LSB, it's actually here. What? This is how we are plotting. And then can we find what is DNL now? So DNL, it is initially, let us okay, now DNL is half now, because whatever is your INL, that will be DNL initially. Then from this would have been here, this would have been here, but it's actually here. So this is now, this is minus 1 LSB. See, this is your bit. When the increment of 1 bit happens at the input, output would have been there here, but it is still here, so it is minus 1 LSB. So taking this as reference, this would have been here, but it is actually here. So how much is above here? Can you see this? From this would have been here, it's actually 1.5 LSB more. This is 1.5 LSB more. And from this would have been here, but it is still here, it is minus 1 LSB. And from this would have been here, it is still here, it's minus 1 LSB. This would have been here, but it's actually here, it's plus 1 LSB. So from this would have been here, but it is there, it's 1.5 LSB more. From this would have been here, but it is 2.5 LSB less, minus 2.5 LSB less. Okay, let me just repeat. This is initially half LSB. Now see, this is where this is minus, this is plus half LSB. From this would have been here, but it's actually here, it's minus 1 LSB. From here, this would have been here for 0 DNL, but it's actually here. So from this to this, it's actually 1.5 LSB. That's why it is 1.5 LSB. And then from this would have been here, but it is here only, it's minus 1 LSB. From this would have been there, but it is still here, minus 1 LSB. From this would have been here, but it is there up, it is 1 LSB more. From this would have been here, but it is there here, so this is 1.5 LSB. From this would have been here, but it is over here. So from here it is 1 to 2.5 LSB less. So let us see the addition. Can you see what is this plus this? So this is actually half plus minus 1 is minus half. So can you see this, what happens? So this half, this will become 2 minus 1 is 2 minus 1 is 1. So here it is 1 minus 1 is 0. Then 0 minus 1 is minus 1. Minus 1 plus 1 is 0. 0 plus 1.5 is 1.5. 1.5 plus minus 2.5 is actually minus 1. So this is perfectly matching. So this way we can able to find what is DNL by writing the graph. Now the question is, okay, in the previous case also we are supposed to find offset error. The offset error is one where if there is a, if you can actually find here, this for the previous one, see when the input is 0 0 0, the output is also at 0 LSB, so there is no offset error. So offset error in this case is 0. Offset error is actually 0 LSB. This is offset error. And what is gain error? So by after making offset error as 0, whatever is the error that happens at the final bit is your gain error. How much is the error here? So if you can see here, whatever is your INL, what is INL at last bit? At last bit after making offset error as 0 is nothing but your gain error. This is gain error. INL at last bit after offset error is made 0 LSB. Since offset error is already 0 LSB, whatever is the INL, that will become the gain error. Repeat. Now since offset error is 0, what is gain error? Gain error is nothing but it is the INL value at the last input bit, that is after the maximum input bit, at the maximum input bits after making offset error 0. Since offset error is initially 0, whatever is your INL at the last bit happens to be the gain error. So in this case, gain error is half LSB. Let us see what is the gain error over here. See now, the initial bit itself has an error of half bit. So here offset error is half bit. So now when you make this bit from here to here, so can you see all the bits will come down by half bit? So then does it mean that this will also come down by half bit upon making this offset error as 0? Once you make this offset error from half LSB to 0, all the outputs will come down by half bit. So this is my actual output, which is 1 LSB down from the expected value. Now it actually comes here after making this is after offset error is set to 0. So how much is the difference now? This is actually 1.5 LSB. That is, gain error is minus 1.5 LSB. This is my gain error. Done. Let us see what is this is. Now this is a binary weighted. This is binary weighted R DAC. We know that this is 2R, 4R, 8R, and this happens to be the LSB. This is next bit, this is the LSB. So the actual output is given by V reference into RF by B1 by 2K, B2 by 5K, and B3 by 6K. To be very frank, if there is an error in this, you can see the weight is not increasing by, of course, this would have been actually 4K, but it is 5K. This would have been 8K, but it is 6K. So there is an error in this values of resistance that has been put. So that error, will it result in any INLDN? That's what we are looking into. So we are trying to find out what is the ideal voltage and what is the actual voltage you are supposed to get. So ideal voltage, so anyhow it is 0 volt for 001. So is it not 220 into 5 divided by 8000. So this would have been 0.1375 volts. So this is minus. Then this is how much? So this is 0.1375 into alpha A. Let me make A as 2. Can you see it is minus 0.275. This is the ideal values. And this is 3 LSB. Calculate for 3 LSBs. It is minus 0.4125. Then it is calculate for 4 LSB, it is minus 0.55. Calculate for 5 LSBs, it is minus 0.6875. Calculate for 6 LSBs, this happens to be minus 0.825. So calculate for 7 LSB, this happens to be minus 0.9625. Fine. So this is the ideal values what we are expecting. The actual values are coming from this. So for LSB, it is 220 into 5. Instead of 8K, I am having it as 6K. Equals divided by 6K. So you can see you have an output voltage of, okay, let me write, okay, for the first one, so it is 0. For first one it is 0. For this it is minus 0.1833. And this is 220 into 5 divided by 5K. 5 exponential 3. Hence it is minus 0.22 volt. Then it's the addition of these two plus 0.1833. It's actually 0.4033 minus, and this is I think this is fine because 2K happens to be 2K, so it will be this value only, minus 0.55. Next it is 0.55 plus this LSB, that is 0.1833. Is it actually minus 0.733? How much is this? This will be 0.55 plus 0.22. It's actually 0.77. How much is this? So this will be 0.77 plus 0.1833. Can you see it is minus 0.9533. So these are the actual values. The error is ideal to the actual value. So it's actually more here. How much is that? It is 183.3 millivolt minus of 137.5 millivolt. It's actually 45.8 millivolts of error. And this is 0.275 minus 0.22. The error is 0.055 millivolts. Okay, this is 0.55 volts. That is 5.5 millivolts. So here it is. Okay, let me write it as 5. No, this is 55 millivolt. Is it 0? That is actually 0.27. It is 275 millivolts minus 220 millivolts. It's actually 55 millivolts. Here it is 412. This is actually error is positive. Here is error is minus 55 millivolt, because you are overestimating. Here you are underestimating. Here also you are underestimating, which is nothing but minus 412.5 minus 403.3. It's actually 9.2 millivolt. So here it is 0. Here you are overestimating it by 733 minus 687.5. It's plus 45.5 millivolt. Here you are again underestimating it by 825 minus 770. You are underestimating by 55 millivolts. Here you are underestimating it by 962.5 minus 955.3. It is 7.2 millivolt. So this is the actual error, that is INL. So if you want to write in terms of LSBs, because what is 1 LSB? 1 LSB is actually 137.5 millivolt. if you can actually see this magnitude, this is 1 LSB. Half LSB happens to be 137.5 divided by 2. It is 68.75 millivolt. This is half LSB. This is 1 LSB. This is ideal half LSB. None of the errors are exceeding this half LSB. Suppose if you are rounding this LSB to this INL to so many half LSBs, since all the voltage difference, whether it is plus or minus, is less than 868.75 millivolts, which is nothing but it is less than half LSB, you can round it off to zero error. Here also it is 0. This is 0, 0, 0, then 0. This is 0, this is 0, 0. So it's rounded up to all nearest half LSB. So if you are taking it as quarter LSB, then it is true. But it is, if you are rounding it up to half LSB, all the errors are less than half LSB, you can say that the INL is 0 INL. But there is some error, but since you are rounding it off to half LSB, the error is 0. The error is 0. INL is 0. Okay, that's it. How we can able to analyze all this stuff of okay, this is straightforward. So you have 16 combinations. Try to find out for 1 LSB. So it is straightforward. You can just do it this way. How do I do it? Okay, you have 16 bits. So starting from B1, B2, B3, B4, the voltages are 0, 0, 0. Okay, these are the input combinations. Next it is 0, 0, 1, 1. Next it is 0, 1, 0, 0. Next it is 0, 1, 0, 1. Next it is 0, 1, 1, 0. Next it is 1, 0. Sorry, 0, 1, 1, 1. Next it is 1, 0, 0, 0. Likewise it goes. So up to 16 combination, because here 1 LSB corresponds to, so here 1 LSB corresponds to 5 by 2 power 4, which is not 5 by 16. So 5 by 16 happens to be, 5 divided by 16 happens to be 0.3125 millivolt. So this actually V naught is 0. Here it is 3125 millivolt. Twice of that, 3 times of that, 4 times of that, 5 times of that. This is 8 times 312.5 millivolt. Likewise, the last one, 111, is actually 15 times 312.5 millivolts. So this will be the output voltage you can, of course, you will be getting ideally from this, from this circuit for all input combinations. Okay, thank you.